Hello everyone, I am Ümit Alkuş. In this video, we will solve one problem about electric charge. A charge Q1 of magnitude positive 2.6 microcoulombs is placed at the origin of a coordinate system. Another charge Q2 of magnitude negative 5.2 microcoulombs is placed at 3 meters and negative 1 meters. These charges are held fixed. Determine the coordinates of a point at which a proton remains in equilibrium. Coulomb constant is K 8.99 times 10 to 9 Newton meter squared over Coulomb squared, and elementary charge is E 1.6 times 10 to negative 19 coulombs. In order to solve the problem, let us first determine the reasonable point at which a proton remains in equilibrium. The proton must be located on the line joining the two charges. You cannot put proton between the charges, because as shown in the case of 2, the Coulomb force on the proton due to Q1 is a repulsive force, and the force on the proton due to Q2 is an attractive force. According to this configuration, the proton moves towards Q2. However, according to the problem, the proton should not move. This type of problems are usually solved by the trial-error approach. For case 3, the force on the proton due to Q1 is a repulsive force, and the force on the proton due to Q2 is an attractive force. According to the problem, the magnitudes of F1 and F2 have to be the same. F1 is found by the formula K times the absolute value of Q1 times the absolute value of the charge of the proton, that is E, over the distance between Q1 and the proton, that is B squared. And the magnitude of F2 is K times the absolute value of Q2 times the absolute value of the charge of the proton, that is E, over the distance between the proton and Q2, that is B minus A squared. Here, K's are cancelled. Also, E's are cancelled. And since the absolute value of Q2 is twice the absolute value of Q1, then we obtain the equality 1 over B squared equals 2 over B minus A squared. If we take the square root of both sides, we obtain 1 over B equals square root of 2 over B minus A, from which we obtain square root of 2 times B equals B minus A, or B times 1 minus square root of 2 equals A. Here, since 1 is less than square root of 2, then 1 minus square root of 2 is negative. And because the distance B is positive, then according to this equality, A should be negative. However, A is a distance, so it cannot be negative. As a result, we say that if you put the proton closer to Q2, case 3, you would see this gives no reasonable solution. So, we must put the proton closer to Q1, as shown in case 1. The force on the proton due to Q1 is a repulsive force, and the force on the proton due to Q2 is an attractive force. If we denote the distances as B and B plus A, because the proton remains in equilibrium, the magnitudes of forces F1 and F2 have to be the same. So we write F1 equals F2. F1 is found by the formula K times the absolute value of Q1 times the absolute value of the charge of the proton, that is E, over B squared. And the magnitude of F2 is K times the absolute value of Q2 times the absolute value of the charge of the proton, that is E, over A plus B squared. Here K's are cancelled, also E's are cancelled, so we are remained with 1 over square root of 2 equals B over B plus A, from which we obtain square root of 2 times B equals B plus A, or B times square root of 2 minus 1 equals A. Then we obtain an expression for B as A over square root of 2 minus 1. Before proceeding, let us find the value of A. From the right triangle in the figure, A is found by the Pythagorean theorem as square root of 10 meters. So B is equal to square root of 10 over square root of 2 minus 1. And the calculation gives 7.6344 meters. Now, according to the figure, the x component of the point is negative b times cosine theta, since it is in the negative x-axis. We know b. However, to find cosine theta, we use the right triangle, so we find it as 3 over square root of 10. Therefore, the x-coordinate is obtained as approximately negative 7.24 meters. And the y component of this point is yp equals positive b times sine theta, since it is in the positive y-axis. We know b. And sine theta is found by the right triangle as 1 over square root of 10. Then the y component of the point at which a proton remains in equilibrium is found by approximately 2.41 meters. Okay, we are done. Thank you for your attention. See you in the next video.